Dear students, welcome to today's lesson. Please recollect that last lesson we discussed about what is biasing. We just recapitulate. Biasing is actually providing a required potential to the base of the BJT or to the gate of a FET so that we get the maximum possible output AC swing and the BJT amplifier works appropriately. So after knowing what is biasing, we now go to the next point, how to do bias. What are the biasing techniques? So when we come to biasing technique, we see biasing is to provide a potential of desired polarity at the base of the common emitter configuration, right? So we go to the next slide. What are the various biasing techniques? Here, we first go to the fixed bias. In the fixed bias, what do you see? Just a resistor R1 is connected to the base. And this provides the required current, base current IBQ, which in turn will provide ICQ. So if we go to this part of the circuit, just one moment. If we go to this part of the circuit from here to here, then this equation is VCC is equal to VB is the reverse voltage here. So VCC minus VBE is equal to R1 IBQ because this base quiescent current flows through this R1 IBQ, which is approximately equal to R1 ICQ by beta. Because ICQ is equal to beta IBQ plus ICBEO, that is reverse current through the base collector junction. If you forget or ignore that, then this equation holds good, R1 ICQ by beta. So what is ICQ? ICQ is VC minus VBE multiplied by beta divided by R1. So this is ICQ. The point is, in our last lesson, I explained to you that you have to decide ICQ or the quiescent collector current looking into the transistor output characteristics as well as the load line. And once you have decided ICQ, this is the value of ICQ in this circuit. Now, the point is here, when you choose the transistor, beta is known approximately. But here you have 1, 2, 3 variables, VCC, VBE, R1, etc. So it is not a mathematical equation to find out ICQ. You have so many variables. So how you play around with these variables so that you come to the desired value of ICQ? Because if you make R1 too large or too less, there are many actions, right? So that we shall learn when we learn the transistor amplifier design. But this equation gives you what is the value of ICQ. Once you have decided VCC, you have decided transistor, which decides the beta, and you decide on the R1. VBE, emitter junction voltage for silicon transistors, you can take 0.2 volt. For germanium transistors, you should take 0.6 volt. This technique is emitter bias. Here, same resistance R1 is here, but there is an additional emitter resistance, right? Once again, if you apply Kirchhoff's voltage law to this circuit, then what I find, VCC is equal to R1 IBQ, because IBQ flows through R1, plus VBE plus RE IEQ. RE, IEQ. IEQ is the quiescent current through the collector, through the emitter. Now, theoretically, quiescent current through the emitter and quiescent current through the collector is different, but practically they are same. You can always take the same. Anyway, from this equation, we find VCC minus VBE is equal to R1 IBQ, we write ICQ by beta plus RE ICQ because we replace IEQ by ICQ. They are very much equal to each other. That makes ICQ within bracket R1 by beta plus RE, that is R1 beta RE by beta. From here, ICQ becomes beta multiplied by VCC minus VBE divided by R1 plus beta RE. Here we have added one more resistor RE. Once again, I repeat, this is not a mathematical equation to decide ICQ, to find out ICQ. This equation gives you that having decided R1 and RE and VCC and beta, what is your ICQ, right? So this is emitter bias. Next is self bias or potential divider bias. Here, you will note that this is the most common configuration of transistor biasing. In fact, more than 90% cases, transistor is biased in this fashion because this technique has some special benefits. Here, a resistor R2 is here, right? And what this resistor R1 and R2 does, R1 and R2 works as a potential divider against VCC and the common. And it provides a voltage VBB here, right? So its equivalent circuit is here. The potential here VBB, just by your potential divided circuit, VBB is equal to VCC, here VCC, divided by R1 plus R2 multiplied by R2. This is VBB value. Now, this potential divider can be replaced by its, for theoretical calculation, can be replaced by its Thevenin equivalent here, a potential source VBB with a resistance RB. The value of this VBB is here. And this resistance RB is R1 R2 in parallel. That is R1 R2 divided by R1 plus R2. Right? So this is the equivalent circuit. Now looking at the equivalent circuit, what is the value of ICQ? Now go to this part of the loop. Right? Here VBB is equal to IBQ multiplied by RB plus VBE, the reverse voltage drop here, plus RE IEQ. You take VBE on the left-hand side, VBB minus VBB is equal to IBQ is ICQ by beta RB plus IEQ is replaced by ICQ because they are more or less same into RE. This is ICQ by beta RB plus beta RE, right? So what is the value of ICQ? ICQ is VBB minus VBE multiplied by beta divided by RB plus beta RE. Once again, having decided upon beta and RB and RE, this will be your value of ICQ. Because when you do go for transistor amplifier design, there are some empirical rules to determine the values of these resistors. And when you determine the values of these resistors, you can calculate ICQ and check whether your ICQ is your desired value. If not, you once again change or alter the values of your resistors, etc. And until you go on doing this trial and error method, until you reach your desired value of ICQ. Next is collector feedback bias. Here, This resistor RC, after this resistor RC, there is a resistance R1. Earlier, this resistance R1 was connected to VCC. Now it is connected to R1. Once again, if you go to this loop, from here to here to here to here to here, go to this loop, the ohmic equation is VCC is equal to what current flows through RC? Through RC, two currents flows. One is ICQ, another is IBQ. So IBQ plus ICQ into RC, plus there is a base emitter junction resistance VBE, plus IBQ, there is a hidden resistance here RB, which is actually base emitter junction resistance. You must have learned in your device class that there is a junction resistance as well as there is a junction potential. This junction resistance is RB. Normally for a diode, for a PN junction, this resistance is something of the order of 20 to 25 ohm. But this value RB is there. So from this equation, you find VCC minus VBE is equal to IBQ plus IBQ into RC plus RB plus ICQ into RC. And IBQ can be written as ICQ by beta, RC plus RB, ICQ RC. So ICQ by beta is, we have RB plus 1 plus beta RC, because this beta will be multiplied by here, 1 plus beta RC. So what is the value of ICQ here? Is beta multiplied by VCC minus VBE divided by RB plus 1 plus beta RC. Once again, having decided the values of RB, RC, VCC, beta, etc., you can calculate what is your value of ICQ and check whether this is the ICQ you wanted. If not, you change the values of your resistances, etc., until you reach to the desired value of ICQ. Next is collector emitter feedback bias. Here, same as the last one, but there is another emitter resistance. So here the equation is VCC is equal to IBQ plus ICQ multiplied by RC, because the two currents flows through RC, plus IBQ RB, which is resistance RB, plus IEQ RE plus junction resistance, right? So once again, VCC minus VBE is equal to IBQ multiplied by RC plus RB plus ICQ RC plus IEQ RE. IBQ is written as ICQ by beta, RC plus RB, and ICQ RC, and IEQ is once again written as ICQ. Collector current is considered same as the emitter current, though theoretically it is not same. This becomes ICQ by beta, and this whole expression RB plus 1 plus beta RC plus beta RE. So if you transpose them, ICQ becomes like this: beta into VCC minus VBE divided by RB plus 1 plus beta RC plus beta RE. These are the various types of biasing techniques. This lesson is just to show you what are the various possible of biasing techniques. What are the various possible biasing techniques, right? Now, once again, as I said, I repeat, the most common biasing technique that we use is the cell biasing or potential divider biasing. Now, in our last lesson, we have learned why do we do biasing and what should be the value of ICQ where you do the biasing. And in today's lesson, we have learned what is the value of ICQ in various configurations. Next day, we shall see another point, which is in your syllabus, that this biasing that you are doing, it has got some temperature effect, aging effect, etc. It's like if you buy a transistor amplifier radio today, after 5 years, the radio performance may not be as good as it is new. That is because the biasing points of various transistors, amplifiers, there will be multiple transistors in a radio amplifier. They all changes little bit here and there. And that is called bias instability. Next day, we shall see how do we measure bias instability and how do we take care of it? And what is the remedy? And today's last slide is, if you do not mind, please subscribe to this channel. Because if you do this, if you do subscribe, I get some enthusiasm, some interest in doing this hard work. Okay, thank you today.